Today we shall discuss some order axioms of set of real numbers, and by using those axioms we shall prove some properties of real numbers. Those are order properties of reals. So first are axioms. Assume that P is a subset of R whose elements will be called positive reals. The set P has following properties. P has following properties. Actually, these which I am going to list are the axioms for P. So last time I have also told you that the properties which doesn't require any proof, which are obvious, are called axioms. So for P we have these two axioms. For each x belongs to R, we have x belongs to P or its additive inverse belongs to P or x is equal to 0. And these are the only possibilities for any real number x. So this I have assumed, this is my first axiom. If I take any x, either that x lies in our subset P or its additive inverse lies in P, or x is a 0 number, additive identity of reals. So these are the only possibilities for any real number x. Second axiom is, if xy belongs to P, then x plus y is in P and x into y is in P. So P is closed under addition and P is closed under multiplication. So these are the two axioms associated with the set P. Now using these two axioms we shall prove some properties of the set of real numbers, and we shall give some ordering to the set of real numbers. Property 1. So my claim is 1 belongs to P. The multiplicative identity 1 belongs to P. So why 1 belongs to P? Proof. We know that 1 can be written as 1 into 1. We also know that 1 can also be written as minus 1 into minus 1. So if 1 does not belong to P, then -1 must belong to P. This was my first axiom. One of the two numbers must belong to P. And the second axiom is P is closed under multiplication. So if minus 1 is in P, then minus 1 into minus 1, which I know is 1, belongs to P. But I have assumed that 1 doesn't belong to P, and this step contradicts this step. So it means this step cannot hold. So 1 belongs to P. So I have proved that multiplicative identity belongs to P. The elements of P will be called the positive real numbers. So I have proved that 1 is a positive real number. Let's go to property 2. So by property 2, since P is closed under addition, it means 1 plus 1, which is 2, this belongs to P. 1 plus 1 plus 1, so on up to n times belongs to P. It means all natural numbers belong to P. Property 3. If X and Y are negative numbers, then XY is a positive number. So XY are negative numbers. Negative means XY are not elements of P. So if a real number is element of P, I will call that number a positive number. If it doesn't lie in P, then it will be either a 0 or negative number. It means their additive inverses are elements of P. If X is a negative number, it means its additive inverse minus X is element of P. Y is a negative number, it means its additive inverse minus P is element of P. So I will prove that product of two negative numbers is a positive number. So given that minus X, which is additive inverse of X, minus Y, which is additive inverse of Y, are in P, by my definition of P, either X is in P or minus X is in P. Since X is not in P, it means minus X is in P. So now apply Closure property of multiplication. So minus X into minus Y, this should belong to P. This implies, in our yesterday's lecture, we have already seen that minus X into minus Y is X into Y, so belong to P. So any element of P is called a positive number, so I have proved that XY is a positive number. If X is a positive number and Y is a negative number, then show that XY is a negative number. X belongs to P and minus Y belongs to P. this is my axiom first. So if y is not in P, then minus y must be in P. Now use Closure property under multiplication for P. This is my axiom 2. So x into minus y should belong to P. And yesterday I have proved that the additive inverse of any number can be written as minus 1 times that number. So this can be written as x into minus 1 into y belongs to P, and this further can be written as minus 1 into xy belongs to P, because real numbers are commutative under multiplication, so these I have computed. Again use the same thing, that minus 1 times a real number gives the additive inverse of that real number. So this is minus of xy belongs to P. If minus of xy belongs to P, it means xy does not belong to P. So this is the axiom of set P. Exactly one of the two numbers, x or minus x, is in P. So if minus xy is in P implies xy is not in P. It means xy is a negative number. So if x is a positive number and y is a negative number, their product is a negative number. This I have proved. Next property we shall prove that square of any number is positive. So this is property 5. X square is a positive number. Show that x square belongs to P. If x is a positive number, this implies by closure property under multiplication, x into x, which is x square, is element of P. So it means if x is positive, the square is positive. And if x is non-zero and it doesn't belong to P, that is x is a negative number, then minus of x will belong to P. By our first axiom, one of the two numbers must belong to P. So now apply closure property under multiplication to minus x. So this implies minus x into minus x belongs to P. But we have already seen that minus x into minus y is xy. So this thing is x into x belongs to P, but x into x is x square belongs to P. So either x is positive, then x square is positive, or when x is negative, then x square is a positive number. So next property, I'll show that multiplicative inverse of a positive number is a positive number. Property 6. So if x is a positive number, then its multiplicative inverse is also a positive number. Solution. So by our axioms of yesterday, axioms of multiplication, we know that x times its multiplicative inverse is the identity element of set of real numbers. But for set of real numbers, that identity element is 1. And we have just shown that this 1 is a positive number. So that is now x times x inverse is a positive number. So if x is a positive number, x inverse is a positive number, then by Closure property of multiplication, x into x inverse is in P. But if x is a positive number and x inverse is a negative number, then we have just proved that positive multiplied by negative is a negative number. So if x inverse doesn't belong to P, then x inverse cannot belong to P. Therefore, x inverse must be a positive number if x is a positive number. Now, using this set of positive reals, we shall now give some order properties on the set of real numbers. So first is assume x belongs to P if and only if x is greater than 0. So this is our axiom for ordering. So any thing belongs to P is a positive real number, and that will be denoted by this symbol: x is greater than or greater than 0. Or if x is greater than 0, it means x is an element of P. Second is x is less than y. This will happen when y minus x is element of P, or if y minus x is element of P, it will mean that this y is greater than x. But y minus x belongs to P. From first axiom, this would mean that y minus x is greater than 0. So these three things will be assumed equal: x less than y, y minus x belongs to P, y minus x greater than 0. All these three things are equivalent. Now it follows from these axioms that if x not equal to 0 is a real number, then either x is greater than 0 or x is less than 0. So either x belongs to P. Now we have got this notation for that sentence: x belongs to P, or x less than 0 if x doesn't belong to P. That is, x is positive number or x is negative number. By using these two axioms, I'll prove certain properties of reals. So remember, first property is x belongs to P if and only if x is greater than 0. Second is when x less than y, this means y minus x is an element of P, or y minus x is greater than 0. So I'll use these axioms to prove some properties of real numbers. So first is show that if x less than y, y less than z, then x is less than z. solution. So x is less than y. This means y minus x is element of P. This was my first axiom. And y less than z implies z minus y is element of P. Now y minus x is element of P, z minus y is element of P. P is closed under addition. P is closed under addition. Therefore, y minus x plus z minus y belongs to P. Now use associative property and commutative property under addition. Bring this y near to this minus y, and these are multiplicative inverses of each other. So we get z minus x belongs to P. But this further implies that x is less than z. So this property is called transitive property of real numbers. If x is less than y, y is less than z, then x is less than z. Show that if x less than y and z greater than 0, this implies x times z is less than y times z. So if we have x less than y and I multiply this inequality with some positive number, then less remains less. How do we prove this? So x less than y implies y minus x is a positive number. Z greater than 0 implies z is a positive number. Now y minus x is in P, z is in P. Now use closure property under multiplication. We get y minus x into z belongs to P. This implies, by using distributive property, yz minus xz is element of P. But if this is element of P, it means this number is greater than this number, or this number is less than this number. Xz is less than yz. This was the result which we wanted to prove. The next result is exercise for you. Show that x less than y and z is a negative number, then xz is greater than yz. So this is exercise for the students. One more exercise is, show that if x less than y, then x plus z is less than y plus z for all z belongs to set of real numbers. These two questions are really easy, which I expect from you to do. Next is, if x less than y, then if I take reciprocal both sides, the sign of inequality changes. So 1 over x becomes greater than 1 over y for all xy in P. Let's see the solution. So we have x less than y. This implies y minus x is an element of P. Also, x, y are two elements of P. It means their product x, y is also an element of P. Since xy inverse, we have just seen that if a number is in P, its multiplicative inverse is also in P. So when xy is in P, its multiplicative inverse, which is 1 over xy, is in P. Now y minus x is in P, 1 over xy is in P. So due to closure property of multiplication, their product is in P. So we get y minus x times, notice that 1 over x is same thing as x inverse, and 1 over y is, this is y inverse. So since x and y commute, so here answer can be x inverse y inverse or y inverse x inverse. It doesn't matter because elements of R are commutative, which we have already seen. So this thing I can write it as x inverse times y inverse. This belongs to P. So xy is in P, its inverse is in P, which can be written as x inverse y inverse. So their product is in P. So now multiply these two, we get using distributive property. When I multiply this with this and then use commutativity of x inverse with y, we get y inverse and y. This will give me the multiplicative identity, which is 1 multiplied by x inverse is x inverse here, minus this multiplied by this is x inverse is identity, times y inverse. So this is y inverse is in P. So but x inverse is 1 by x minus 1 by y is in P. So if A minus B is in P, it means this number is greater than this number. It means, or this number is less than this number. 1 over y is less than 1 by x. So this we wanted to prove. When x is less than y, the reciprocal of x, 1 over x, will become greater than 1 over y. So this is the all for today.